Space remains an endless frontier of mysteries and unresolved puzzles. Among these mysteries lies the exploration of exoplanets, worlds vastly different from our own. Picture a place where molten glass rains sideways at speeds surpassing those of a jet, or imagine a planet so close to its star that it's gradually being torn apart, its atmosphere consumed piece by piece. This may sound like science fiction, but it's part of the chillingly real realm of exoplanets. Today, we'll dive deep into the blazing heat of one exoplanet and the doomed fate of another. Prepare to have your mind expanded as we journey to these alien worlds, where the familiar laws of physics are pushed to their extremes. One especially intriguing exoplanet, HD 189733b, or as we'll call it, 33b, was discovered orbiting a star in the constellation Vulpecula. This discovery was pivotal, broadening our knowledge of distant planetary systems. A team led by the French astronomer François Bouchy made this extraordinary find, using the LED spectrograph at the Observatoire de Haute-Provence in France. Classified as a hot Jupiter, this gas giant orbits extremely close to its parent star, experiencing scorching temperatures that create diverse and intense atmospheric phenomena. These unusual conditions have made 33b a fascinating subject for astronomers worldwide. The radial velocity method, which detects slight wobbles in a star caused by an orbiting planet's gravitational influence, led to this planet's discovery in October 2005. HD 33b quickly gained prominence within the astronomical community. What makes this exoplanet particularly intriguing is its transit across its host star from our viewpoint on Earth. This transit enables detailed atmospheric analysis through transmission spectroscopy, helping scientists conduct extensive studies of HD 33b. Such observations have made it one of the most thoroughly examined exoplanets to date, providing invaluable insights into the properties and behaviors of atmospheres beyond our solar system. Following our discussion of 33b's discovery and early observations, let's explore the traits that make it a standout subject in the study of planetary atmospheres. Situated approximately 64 light-years away in the constellation Vulpecula, this exoplanet is a prime example of the extreme conditions possible on distant gas giants. It orbits its host star every 2.2 Earth days, a proximity that heavily influences its atmospheric activity and intense visual appearance. HD 33b's atmosphere is rich in silica particles, which gives it a vivid azure blue hue similar to Earth's appearance from space. However, any resemblance to Earth ends here, as the environmental conditions on HD 33b are vastly more severe than anything we experience. This exoplanet serves as a remarkable reminder of the diversity and extremity found in our universe, challenging our understanding of planetary science and the possibilities of worlds beyond. Extreme temperatures and pressures on HD 33b cause silicate materials to condense into clouds, scattering blue light and creating an ethereal, striking celestial view. When it comes to weather, HD 33b is truly extraordinary. The planet experiences wind speeds reaching 5,400 miles per hour, far exceeding any earthly aircraft and clocking in at 7 times the speed of sound. These ferocious winds carry molten glass, formed from silicate heated by the star's intense proximity, and rain it sideways in a blistering, nearly apocalyptic storm. Daytime temperatures soar beyond 1,000 degrees Celsius, hot enough to vaporize metals, while even the night side, though somewhat cooler, remains intensely hot. This dramatic difference in temperature between the planet's day and night sides drives its powerful wind patterns, as heat is redistributed across the planet. Comparing this to Earth's atmospheric dynamics, the winds on this hot Jupiter dwarf even the strongest hurricane force winds, such as those in Hurricane Patricia of 2015, which reached a peak of about 215 miles per hour. This extreme contrast underscores the immense power of HD 33b's atmosphere. A particularly fascinating theory about HD 33b involves the possible role of its magnetic field, if one exists. A magnetic field could influence atmospheric dynamics by channeling particles and potentially interacting with stellar winds from the host star. Such interactions might even strip away the atmosphere over time or produce aurora-like displays far more intense than those on Earth. HD 33b's regular transits across its star make it ideal for close atmospheric study through spectroscopy, allowing astronomers to analyze its atmospheric composition and behavior in unprecedented detail. This wealth of data has made HD 33b one of the best-studied hot Jupiters and a cornerstone subject in exoplanetary science. Continuing our journey into the fascinating realm of exoplanets, we encounter yet another remarkable discovery, WASP-12b, which we'll refer to as 12b. Discovered as part of the Wide-Angle Search for Planets (WASP) project, this exoplanet demonstrates the severe conditions faced by planets that orbit extremely close to their host stars. A team led by British astronomer Don Polacco from Queen's University Belfast identified this planet, which is classified as a hot Jupiter, a gas giant similar in size to Jupiter but orbiting at a much closer distance from its star, resulting in extreme surface temperatures. The discovery of 12b took place at the Super WASP North Observatory in the Canary Islands, Spain, a key facility in the WASP project. This observatory uses the transit method to detect planets by observing slight decreases in a star's brightness as a planet crosses in front of it. Such transits provide astronomers with essential data, revealing not only the existence of new exoplanets but also offering insights into their properties. In 2008, the discovery of WASP-12b was officially announced, with its details published in a paper that same year. The rapid detection and reporting of this planet underscore the effectiveness of the transit photometry method used by the WASP project. WASP-12b's close orbit to its host star results in some of the harshest conditions observed on any exoplanet. The intense gravitational pull from the star distorts the planet, stretching it into an elongated shape, while the searing temperatures define its extreme environment. This exoplanet stands as a reminder of the diversity and hostility often found in distant planetary systems, offering invaluable insights into the dynamics of exoplanetary interactions. Located about 600 light-years away in the constellation Auriga, WASP-12b, often called a doomed planet, vividly displays the dramatic impacts of intense stellar influence. This gas giant has about 1.4 times Jupiter's mass but has expanded to a radius over 1.9 times larger due to the extreme heating from its nearby star. The planet orbits at just 2% of the distance between Earth and the Sun, roughly 3.4 million kilometers, resulting in an orbital period of approximately 26 hours. A year on WASP-12b is only slightly longer than a day on Earth. The atmospheric conditions on this doomed planet are among the most hostile known, with temperatures exceeding 2,500 degrees Celsius. This extreme heat provides enough energy for atmospheric particles to escape the planet's gravity, leading to significant atmospheric loss over time. Furthermore, the intense gravitational pull from its star causes WASP-12b to assume an elongated, egg-like shape, impacting both its atmospheric and surface dynamics. The situation of WASP-12b closely aligns with the Roche limit in celestial mechanics, a theoretical threshold that describes the distance within which a satellite would disintegrate under the tidal forces of its primary planet. In WASP-12b's case, it faces a similar fate, not disintegrating into a ring system like a moon might, but slowly being drawn into its star. An interesting hypothesis concerning WASP-12b involves the presence of a dense, dark material on its star-facing side, possibly made up of heavier molecules altered by the extreme heat and driven to the star-facing side by powerful atmospheric winds. This dark material could absorb more starlight, intensifying the heating and hastening the planet's destruction. The inevitable fate of WASP-12b offers crucial insights for scientists studying the processes of planetary formation and breakdown. Observations reveal an unusually high amount of carbon in its atmosphere, more than oxygen, suggesting that carbon-rich planets might be more common than previously thought. This discovery could reshape our understanding of planetary formation and the types of dominant chemicals in their atmospheres.